Okay guys, Assalamualaikum warahmatullahi wabarakatuh. Now we are going to discuss the example of single phase induction motor, which the question already being highlighted in the notes. It was given that this question is just like the question inside the example of your lecture or your textbook, but we amend a few details so that you can practice on the example and then again repeat the same question with the different parameters inside this example. Okay, first of all, when you have this kind of question, what you have to do is that just same like previous steps on the chapter 2 and chapter DC machine, and also that generator and motor and generator. So first of all, you have is that you transfer all the parameters given here into circuit. So what you have to do is that you write down all the related circuit of the single phase induction motor, and resistor here, the inductor here, R1, J1, and you may pause this slide if necessary. So write down all the list down all the parameters related. We have R1, JX1, JX2 here, magnetizing circuit. So all the related equivalent circuit parameters you key in into the drawing. Okay, the first part is the forward parameters, which is 0.5 R2, and second one is 0.5 R2 over 2 minus S, 6 value. Okay, so we have here R1, JX1, 0.5, half of it, because we already distribute into two, split into two. We have forward and backward. So when we have our motor here, so this is our rotor, this is our stator. So this phase, this pole will become north and south alternately. When the forward part, let's say we have a positive cycles of the voltage, single phase current and voltage here comes in, this one become north, this one become south. When we are forward filling or the circuit facing this negative cycles, so this one become south, this one become north. So this is so-called forward, this is so-called backward or reverse of the system. So we split into two. This is for forward, this is for backward. Okay, from this circuit we have to get the what so-called the Thevenin equivalent impedance of the system. So like what we have explained inside the notes, what you have to do is that this part, instead of you maintain like this, so you have to transfer into Thevenin equivalent circuit of your, forgive me for the drawing. So instead of 0.5 ZF here, you have to get the Thevenin equivalent circuit of R forward and JX forward, and for this Thevenin equivalent impedance. Same goes to the negative part. So you have to acquire or calculate and obtain the R backward with the JX backward, sorry, this B. So you have to transfer all of this into Thevenin equivalent impedance, and also this part into Thevenin equivalent impedance. Okay, as I mentioned to you before, what we have to do is that from the statement that we have, we transfer into circuit. We draw the circuit, we list down all the parameters, and we list down all the scenario. So the scenario is that we have the system with 110 volts of incoming, with 2/3 of the motor rating, which is 2/3 horsepower. We can convert into 1 horsepower is equal to 746 watts per horsepower. So directly you can convert, or you just list down first. So 6 pole, 50 Hz environment. What else? And also we have to list down all the parameter value of your R1 value and X1 value, X2 value, and the magnetizing value. We list down in the circuit. So later means that you don't have to revise or review anymore on the statement. So it's easy to visualize based on circuit. So that's the tips lah. So once you get the statement or the parameters, you just transfer into circuit. So we have here all the value of the R1, R2, magnetizing value, impedance, inductance, the incoming voltage, power rating, whatsoever. You list this down, and then only we list what is the requirement or the things that we need to calculate. So first of all, we being mentioned about or being asked about the speed. What is the speed and speed of the motor or the shaft? And so in terms of speed, and so the speed here, we have two speed. One is synchronous speed, which is ns. So same with single phase and your three phase, and the speed is the same. So for the synchronous speed, so S synchronous speed, the frequency is your electrical signal here. It comes in 50 Hz, so you put 50 Hz. If it comes in 60 Hz, you put 60 Hz. For this system, we have 50 Hz. So 120 times 50 divided by how many poles of the system? So 6 poles. Even though we have two single phase, we might have a few stopping points of the system. Whereby here, if we have like this, so this is 2 poles. If we have another part or pair of poles, so we have here 4 poles. Let's say we arrange the system with this kind of arrangement, so we have 6 poles. So this motor comes with 6 poles. So 1 divided by 6, so you will get 1000 rotation per minute RPM of the system. This is for your synchronous speed. Meanwhile, for your mechanical speed or shaft speed, and for sure, like I explained to you before, if we playing a kite, so we have to drag the kite so that the kite can fly. And I explained regarding the kite before. So you will have to pull the kite and towards the wind direction, so the kite can uplifted. So for sure the kite have to follow you rather than you follow the kite kan. And wow, layang-layang ni. So you have to drag the kite towards the wind direction so the kite can lift upward. So for sure you have to have some slip. Means that the rotation of your mechanical shaft will follow your electrical frequency or electrical cycle in certain gap. So mechanical speed is equal to 1 minus slip times your speed, synchronous speed. So 1 minus, which is 7%, 0.07 or 7/100 times 1000. So you will get 930 RPM of your mechanical speed. And so this is your mechanical speed or your shaft speed. And it will follow the electrical cycles or electrical frequency. So this is 930 rotation per minute. And so settle for question number 1. Okay, next in B, we need to calculate what is the stator current. So the stator current, which is the current that flows into your system, which is I in or I1. And here, so actually I in is equal to V in divided by Z in. Or we have Ohm's law, which is V equal to IR. So you can reshuffle all of these attributes. If you want to find what V, so V is equal to IR. So if you want to find I, so I is equal to V over R. So I equal to V over R, or V over impedance. V across here, which is 110 volt, divided by the overall impedance here. So you have to find the overall Thevenin impedance across the whole circuit. So we have here I stator equal to V in divided by the overall impedance of the system, which is R1 plus JX1 plus here the 0.5 and the forward impedance of forward 0.5, half of it. Another half is the impedance of the ZB, Z backward here, and impedance of Z backward here. So half of impedance in the forward, half of the impedance in the backward. And okay, so we find first what is the ZF. So as I told you before, we transfer the circuit of this part and this part into the over here into Z forward and Z forward. You draw the circuit of your equivalent Thevenins and expected equivalent Thevenins. We have here inductor, resistor, and your magnetizing, and this is your JX2. This is your R2 here. So transfer into Z forward, and so you have to do the parallel mixing of these two elements. Okay, so if we put into into mathematical equivalent, so we shall have a Z forward equal to R2 over S here plus JX2 and JXM divided by, and this is parallel equation. So times, here we have to times it. On the below part we have to plus all together, JX2 plus JXM. So from the values here we put into the system. So R2 is 3.13. Usually inside your calculation, for me itself, this is the part where we usually make a mistake, and we use our calculator inside our calculation here, but there is a typo error or missing parts that you do mistake. So be careful here. 1.56. You have to calculate and solve part by part. You punch into your system or your calculator and solve part by part. Okay, that's better. So J58.2. Yeah. So the above one, this one is times, not plus, times. So the lower one, all are plus together. 3.13 0